Hello, my name is Paul Jarrell, and this is my submission for the Congress of Future Medical Leaders Scholarship Challenge. In November 2014, I attended the Congress of Future Medical Leaders and Scholars in Washington, D.C. While there, I had the privilege of listening to many amazing speakers, but I was most inspired by Ebola survivor Dr. Richard Sacra. Throughout his presentation, Sacra motivated us on fueling ourselves with our passion. His advice resonated deeply with me, and on my flight back to Austin, I began to wonder what my own passion was. After reflecting, I concluded that my passion is my family. 13 years ago, my mom was pregnant with my youngest sister, Leah. At the time, my mom was a programmer and spent most of her day working in front of her computer. As Leah developed, my mom noticed a sharp pain in her right thigh, and after an appointment with her doctor, she was diagnosed with deep vein thrombosis, or DVT. Deep vein thrombosis is caused when blood platelets stick together and form a clot. Blood clots restrict the flow of blood and can cause pain and swelling to occur. Not only can DVTs affect a patient's quality of life, but it can also become fatal. Blood clots are at risk of breaking off, traveling through the bloodstream, lodging in the lungs, and blocking blood flow. This is called a pulmonary embolism. Doctors treat deep vein thrombosis by prescribing blood thinners in an attempt to dissolve the clots. After a cycle of these blood thinners, my mom's condition had improved. After 3 years, my mom felt another sharp pain in the same location because her clot had reoccurred. Doctors informed her that she had a condition called peripheral vascular disease. Peripheral vascular disease is the damage or hardening of the endothelial layer of a vein, causing blood platelets to build up and form clots. My mom's doctor believed that her first clot may have caused this irreversible damage and informed her that she will remain on blood thinners for the rest of her life. After the Congress, I began pondering solutions to my mom's condition. After speaking with some teachers and researching online, I began to develop my hypothesis. If I can devise a method to tissue engineer a vein, I can solve peripheral vascular disease by replacing the damaged area. My tissue engineering method consists of two phases: decellularization and recellularization. My vein graft begins with the removal of a section of a femoral vein from a deceased donor. The vein must be healthy and undamaged because it will be the foundation for the tissue. All of the tissues in an organism are made up of two parts: cells and the extracellular matrix. Here's an analogy. Picture all the cells in your body as living people. The ECM would be the building they live in. The extracellular matrix is the non-living structure made up of mostly collagen, protoglycans, lamina, and fibronectin, and it is responsible for giving tissues their shape and their function. Decellularization is the process in which all living cells are removed, leaving the ECM scaffold. Venous tissue is very delicate, so in order to lyse or break down the cells without damaging the extracellular matrix, I will use a Zwitter ionic detergent. Zwitter ionic detergents, such as calamido propyl dimethamonio propane sulfate, or CHAPS for short, are very special because they have properties of both ionic and non-ionic detergents. CHAPS dissolve cells and nucleic membranes while effectively removing cells with minimal damage to the ECM. The vein tissue will be perfused with the detergent and rinsed with deionized water repeatedly until all cells are removed, leaving behind a bare ECM. Phase 2, recellularization, utilizes induced pluripotent stem cells and their amazing properties. iPS cells, a form of stem cell, have the potential to develop into many specialized cell types and serve as an internal repair system for the body. iPS cells were first discovered by Dr. Shinya Yamanaka and Dr. James A. Thompson when they used a virus to manipulate a cell's genetic information, forcing it to express traits of an embryonic stem cell. The discovery of iPSs ended the once controversial debate over the moral use of stem cells because embryos were no longer required. The next step in my design requires a sample of vein tissue removed from the patient in order to be reprogrammed into iPS cells. Because the use of viral vectors raises the risk of cancer, the graft will utilize tiny circular pieces of DNA called plasmids. These plasmids will carry genetic information into the cell and reprogram it. Similar to the viral method, only the cell's genome won't be altered at all. The newly formed iPS cells will be co-cultured with more vein cells in vitro and seeded into the bare extracellular matrix from phase 1. Next, the tissue will be incubated in a perfusion bioreactor, which supplies the growing cells with nutrients and oxygen. Because oxygen has a low solubility, it must be continuously perfused over the cells. Once the tissue is fully grown, it will be surgically grafted, replacing the damaged vein. While researching, I came across a major setback. Vein grafts have a high chance of failure. When a graft is transplanted into a patient, the body begins healing and integrating the new piece in. Sometimes the body over-remodels and the vein can become too thick, restricting blood flow again. As I researched, I found that 40% of all grafts develop this form of failure. I stumbled upon Dr. Manfred Boehm's work in the NIH's National Heart, Lung, and Blood Institute. Dr. Boehm is researching the causes of graft failure and has discovered it is caused by a process called endothelial to mesenchymal transition, or endo-MT. During endo-MT, the innermost layer of the vein, the endothelium, begins to develop into fibrous mesenchymal cells, which causes the graft to thicken and restrict blood flow. Boehm has also discovered that this process is caused by TGF-beta, a protein expressed soon after transplantation. Boehm suggests that one possible treatment is a blood pressure medicine called losartan. Losartan inhibits the TGF-beta protein, therefore eliminating endo-MT. In conclusion, by combining the decellularization and recellularization process in Dr. Boehm's research, I can design an extremely effective vein graft. Not only does my theory solve PVD, but it also opens the field of tissue engineering for further experimentation and research. I would like to say thank you to all the people who helped me on this project. Thank you, Mom and Dad, thank you, teachers, and thank you, friends. I would like to also thank Richard Rossi and all the people at the Congress. You guys have supplied me with an amazing opportunity, and I'd want to say thank you.